Yeah, your voice is breaking in between. So thank you very much, Mr. Dominic. Welcome all participants. As usual, we have a lot of participants today. I think it is going to able to cross 100 plus. So we are successfully running our programs with an average participation of 200 to 225 in last days. So today we are going to discuss about SPD's surge protection device, part 2 of surge protection device. Please understand that the first part we discussed some points of SPDs, and today we are going to discuss about, or I'm going to explain the methods of some methods which which is used to select the current rating of type 1 SPD, as well as some techniques of selection of SPDs based on voltage protection level, selection based on temporary overvoltage, and so on. Only 3 or 4 subjects from the SPDs will be selected or will be discussed today. But all of us should understand that in comparison to our webinars for fire due to short circuit or electrical safety or the lightning protection, the subject of SPD is little bit tough to understand. In the sense, this is the SPD is number one. It's a new concept or new product in the market. Of course, not new. For 20 years, it's there, but mostly for users, it's still a new product. It's not like MCBs or other protective switch gears, which is used in the electrical market. So as a result, also the SPDs are connected in parallel to the circuit. As a result, in case of any failure in your SPD, the installed site is going to have problem. So in comparison to the other protective devices such as fuse MCBs, selection of SPD is very critical because this device is connected in parallel, and number 2, this device is at the end of life, this device is going to create a short circuit. So it's very critical to select SPD. So as I said, in comparison to our the other programs, this subject will be little bit tough to understand because it's a different kind of tough subject. Now let me start the presentation. The standards of SPDs, there are 2 series of standards published by IEC. Of course, the 61643, 1112 for power line, 2122 for data and signal line, 3132 for solar PV. Out of that, this 11 and 12 has been accepted as an Indian standard. IS 16463, it's not 61643, but 16463 is the IS number. Of course, not the latest one. For example, part 12, 2020, there is an upgraded version has been published by the IEC, but the Indian standard is little bit from the old IEC. We also have the IEC 60364. What I am going to refer is from both these standards, 60364 2020 and 61643 2020. As I always say, the concept of protection is equipotential bonding. If you are able to make a very good equipotential bonding, you achieve very good safety against electric shock, safety against touch voltages. Your electronic equipment will be perfect. Your electrical installation will be perfect. So a good earthing means creating a very good equipotential bonding. That means there is no potential difference between different parts of an installation. As a result, there is no failure. In the last webinar, we discussed about voltage impulse withstanding capacity. What does it means? The electrical items connected to a 230 or a 400 volt line has been categorized into 4. Example, category 4, 6 kV, category 3, 4 kV, category 2, 2.5 kV, and category 1, 1.5 kV. These are the impulse voltages with which the equipment is able to withstand for a short time. 1.2 to 50 microseconds voltage impulse test is the basic test which is carried out to find out its impulse withstanding capacity. Once when the power line crosses each and every part of the zone, like with respect to lightning protection, the building is classified into zone 0, zone 1, LPZ1, LPZ2, and LPZ3. With respect to electrical safety, at the mains incoming panel, we are supposed to have the main protective equipotential bonding. At the sub switchboard, probably supplementary equipotential bonding, and so on. So basically, this is the concept with respect to SPD. The most important point is the voltage impulse withstanding capacity. Means every electrical apparatus is able to withstand a certain voltage. Its insulation is limited and it cannot, equipment cannot withstand a high voltage, example 10 kV, 20 kV. That is not possible. So the maximum is shown here. Now, with respect to lightning, there are two wave shapes which we always refer. The first one, 10 by 350 microseconds wave shape. It is called as the impulse current wave shape, which is nothing but the energy equivalence of a lightning current has been generated in a laboratory as a current impulse in the shape of 10 by 350 microseconds. Means the current goes from 0 to peak in 10 microseconds and comes to half of the peak in 350 microseconds. This is the equivalent energy contained in a lightning strike. But as I always say, don't think that lightning is always 10 by 350. It is not like that. It is a current impulse generated or produced in a laboratory for the purpose of testing the equipments or testing the components. Similarly, we have one more wave shape, which is the 8 by 20 microseconds, means the discharge current. The current goes from 0 to peak in 8 microseconds and comes to half value in 20 microseconds. So these two wave shapes you always should keep in mind. The building is classified into various lightning protection zone. For example, outside the building, you have lightning protection zone 0, which is subdivided into, you can see here, LPZ0, LPZ0A, 0E, 0B, like that. Depending upon the severity of the current, lightning current flowing through the building, the lightning protection is, the building is classified into lightning protection zone. A zone inside LPZ1 is a protected place where there is no direct lightning current and the voltage impulses are further reduced. LPZ2 is further inside the building where the threats are further reduced. LPZ3 is further reduced place. Like that, a building can be classified into several lightning protection zones. N number of zones can be created depending upon what kind of protection you are looking for. Example, lightning protection zone 0, no protection and maximum electromagnetic impulses can be expected. Zone 1 is there is no limited EMI and the UW voltage impulse withstand is 4 kV. Like that, each zone, the voltage impulses are specified. Once when a power line goes from out, once when it comes into the building, you can see here there is a transformer. From the transformer, power line is connected up to the last equipment. Once when the power line crosses each and every zone, we are supposed to create equipotential bonding between the live conductors or current carrying conductors and the earth. Earth means the earth bus bar of that particular panel. So at the first one, at the power line incoming, type 1 SPD, power line in the sub switchboard, probably type 2 SPD and type 3 SPD. So this is basically the recommended practice of making equipotential bonding. That means the building is classified into several steps and the lightning threat is reduced into several steps. In a power line, for example, at the main distribution board, at the origin of installation, whatever the SPD which we are using. Now, in the figure, what you are seeing is you have a transformer, you have a line coming from the transformer, the three-phase and the neutral, it goes up to the last equipment. You have the at or near the origin of installation, distribution circuits and close to sensitive equipment. The first is at the origin of installation, you are connecting an SPD. It can be a type 1 or a type 2 SPD, and is applicable to reduce the voltage protection level, or is applicable in some cases you really don't need a type 1 SPD, you can go for a type 2 SPD. Similarly, at the sub switchboard, you are supposed to have either a type 2 SPD or a type 3 SPD. It depends on the severity which you are, or the protection severity which you are looking for. Similarly, for near to the sensitive equipment, you can also go for a type 2 SPD or a type 3 SPD. So basically, this is how SPDs are selected and installed in the electrical network. Today, we will be looking at the criteria, some of the criteria with which at the origin of installation, how at the origin of installation means at the main distribution board, type 1 or type 2, what is the criteria? Plus, if it is a type 1 SPD, what is the current rating of the SPD? Will be explained in the next slides. Now you must understand that you are seeing a building. In the building, you have electrical apparatus. The power is coming from the overhead line. The source of lightning or the lightning threat has been classified into 4 types in the IEC 62305. S1 stands for flash to the structure, means a direct lightning strike. Where I am moving the cursor, a direct lightning strike is on the building. As a result, this strike is going to create a failure. Number 2, S2, flash near the structure. Here, direct lightning is striking near the building. As a result, the induced defect, the coupled defect, are going to kill the electronics inside the building. Number 3, sorry, this is not S1, it is S3, flash to the service, means you have a overhead line and there is a direct lightning strike on the overhead line. Current may enter into your building through the service line. And the fourth one, this is S4, not S2. Actually, S1, S2, S3, S4. S4 is flash near the structure. That means, flash near the service. That means near the power line, you have a lightning strike. So these are the 4 different type of threats. S1 stands for direct strike on the building, S2 near the building, S3 on the service, S4 near to the service. These 4 threats are going to create failure in your building, and in order to protect your electrical and electronic equipment at the origin of installation, that means at the main distribution board, here you can see at the main distribution board, we are supposed to create a equipotential bonding with the help of an SPD. How in this particular case, you can see a picture with a 3-phase RYB, neutral, PE conductor. Typically, 4 SPDs are connected in parallel, 3 numbers between the 3 line conductors to neutral and 1 SPD between neutral and the earth. Imagine there is a direct lightning strike probably on the building or closer to the building. As a result, the earth potential is going up and ground potential rise is happening. The potential of the earth conductor is suddenly going to a high level. As a result, this particular SPD, as I explained in the last presentation, SPDs are having a parameter called as voltage protection level. Once when these are voltage operated devices, non-linear devices, and once when the voltage crosses certain limit, it offers a very low impedance. Imagine the protection level is 1.5 kV. Once when the potential difference between N and P reaches 1.5 kV, the first device operates and it connects the neutral and the earth together. As a result, equipotential bonding is created within few nanoseconds. So the next moment, there is a high potential between neutral and the other lines. As a result, the other 3 SPD also operate and it creates a perfect equipotential bonding. And this whole equipotential bonding happens within nanoseconds. So basically, the first part, even if we say that SPDs are diverting current, but before diverting current, it is creating a bonding. Then the current is diverted. Now, imagine you have a set of SPD at the origin of installation. Now, from the origin of installation up to the load, if the length of the line are YB, neutral, and the PE conductor, if the length of the line is equal, and if these lines, the three-phase, neutral, and the PE conductor, if there is no chance for additional coupling, your equipment is protected, because between the terminals of the equipment, there is no higher voltage. Imagine you have a class 3 equipment which can withstand, let us say, 4 kV voltage impulse. And when the SPDs are operating, actually the voltage between line to neutral or line to line and neutral to earth, these voltages are much, much lower than 4 kV. Say, for example, in an ideal case, zero potential, 0 volt, all are equipotentially bonded. As a result, your equipment is safe. There is no potential difference between different terminals of the equipment. As a result, the equipment is safe. But please remember the condition. The line length from the SPD, line, neutral, and the earth, these shall be similar, and there is no induced part. The lightning is not going to create any induced effect between the lines. Under that condition, we have a safe installation, our equipment is protected. But for example, if the earth wire is not running parallel, or if the earth wire is running through a different route, and if there are large loops in the secondary side of the downstream, the SPD, of course, your equipment is not really protected. You need to have devices closer to the equipment as well. Then what happens? If we look at towards the source, the transformer neutral is connected to an earth electrode far away, an earthing system far away from your electrical installation. As a result, the reference of the phase and the neutral are from this faraway place, which is having a different potential with respect to your building. As a result, the current will try to flow towards the source of the power supply. It goes to the source, and a part of this current goes to probably through the neutral earthing, and so on. It also gets dissipated as heat in the conductor. So this is how basically SPD operates. So basically, at your origin of installation, you need an SPD, and most often the incoming equipment are protected under several conditions we need to fulfill. Mostly fulfilling these conditions are quite difficult. The current goes towards the source. Basically, whatever the threat which is supposed to happen to your building, the SPD is diverting the current towards the source. As a result, your equipment are protected. Now, how the current, what is the capacity? For example, now I have told you the SPDs are diverting the current to the source. What is the capacity? How much current is expected, and how much current these SPDs are supposed to divert is a big question always. In the picture, you are seeing a building with a lightning is striking the building. A proper equipotential bonding is made on the building. There is a equipotential bonding at the power line incoming, and you have a long service. Imagine the transformer is 1 kilometer away from your building, and you are having an overhead line at the origin of installation. Main distribution board, we have the SPD, and equipotential bonding is made. Under this condition, the IEC is recommending that about 50% of the current, of the total current, goes to earth, and approximately 50% of the total current gets diverted to the connected service. There can be several connected service. One of the connected service is the power line. The other connected services are, say, for example, in Bombay, the most of the housing colonies, they have the connected metallic pipeline for gas. Similarly, there can be metal pipeline for water supply, sewage supply, and so on. So 50% of the current, lightning current, will be diverted to the connected service. But for the calculation of the rating of SPD, we consider that 50% of this current is diverted to the power line, because most of the time we don't have any other metallic services in our country, because most of the water supply, sewage, these are nowadays plastic or PVC. So the assumed values are 50% of the current flows to earth and 50% flows to the connected metallic service, provided there is a long service cable. If there is no service connected, then of course this 50% you have to neglect because there is no way. With this calculation, imagine all of you know very well that during our last 2 webinars, we explained lightning protection level. There are 4 classes or 4 levels of lightning protection, LPL 1, 2, 3, 4. 1 stands for a maximum current of 200 kiloampere, 2 stands for a maximum current of 150 kiloampere, 3 stands for a maximum current of 100 kiloampere. 50% of this total current is diverted to the service if there is only one service, 100 kiloampere, 75 and 50 kiloampere respectively. If you have 2 service, again the current is getting reduced. If you have 3 service, again further your current is reduced. Where this is applicable is, imagine you have a large industrial or a commercial building where you have 3 transformers. Under that condition, you have to take the calculation I impulse 3 lines because the current through each line may be lesser, but we also should consider the impedances and we also should consider the distances, line impedances and so on. But in practice, the current is diverted to the service, and if you have more number of services, the current through each of the services is less. But generally, for our calculation or for our selection, we select 50% of the current flows through the 230 or 400 volt power line and about 5% through the telephone line. This is the thumb rule which is always used. You also should understand that in large buildings, let's say, for example, industrial buildings or in nowadays the commercial buildings, multi-storied buildings, the transformer is always a part of the building, which is inside the building. And under this condition, if the equipotential bonding is properly made along with the neutral earthing, along with the body earthing of the transformer, actually, the current, there is no low voltage service line connected. The service which is coming from the outside transformer or from the service company or from the electricity supply company, it's a high voltage supply. It's not a low voltage supply. Under this condition, you have no route to divert the 100% or 50% of the current through the low voltage power supply, because there is no low voltage power supply connected to the building. In that condition, type 2 SPD is enough. You don't need to go for a type 1 SPD because the current diversion is actually happening through the high voltage line. Your high voltage, the 11 kV or the 22 kV surge arrestor has to be stronger enough to handle that particular current. With respect to low voltage supply, you can be happy with a type 2 SPD. Another criteria, for example, imagine your building doesn't have a lightning protection system. When we make the risk assessment, we have to find out what minimum protection is required. And in this particular case, the building doesn't need any external lightning protection system. And imagine the power supply is coming from the transformer through underground cable. No lightning protection for the building means the current, 50% of the current which is going to be diverted to the power line, we don't need to consider. No overhead line or it is completely buried under the ground means the direct lightning strike on the service is also not expected. Under this condition, a type 2 SPD at the service entrance is enough. The next condition, your building doesn't have any lightning protection system, but you have an overhead low voltage power supply. And if there is a chance of lightning strike between the building and the last service pole, the expected current is specified in the standard. For example, there are 2 types of connections, CT1, CT2, but what you can just look at the ratings. Say, for example, CT2, that means 3+1 connection, 3-phase supply, 5 kiloampere between line to neutral and 20 kiloampere between neutral and the earth. These ratings are very much specified in the standard. For example, you can refer the IEC 60364 553. The next part In a building, if the cost of electrical installation is not more than 5 times the cost of the SPD, then installing an SPD is not economical. Let's say, for example, a small building. There is only some tube lights or lights and the fan. The cost of the total electrical installation is less than 25,000 rupees. And if you wanted to put the SPD, and if the SPD's cost is 5,000, it's better not to put the SPD because it's not economical. So like this, the rating of the SPD can be selected, especially the SPD which is at the power line incoming, can be selected based on various conditions. I'm not going to explain all the conditions because it takes a lot of time, because that current selection itself probably make a lot of time. So these are some of the examples. Similarly, the next example, with respect to voltage protection level, as I said, every equipment has got a voltage impulse withstanding capacity. The wiring has got certain withstanding capacity, the equipment has got certain withstanding capacity, the panel board has got certain withstanding capacity. Your SPD is having a parameter called the voltage protection level. Now, there is a parameter called the effective protection level. What does it mean is, between the point A and B, we are connecting an SPD in parallel through wires, through a fuse. D stands for a fuse, to the next part B. The electrical equivalent circuit will be something like this. So during a transient current flow, your line length is equal to an impedance. Your fuse also has got a certain impedance. In between, the line L2 has got an impedance. As a result, during a transient current flow or during a surge current flow, the actual voltage protection level between A and B, because your equipment is connected between A and B, you are not bothered about the protection level of the SPD rather than the protection level of SPD. You have to be bothered about the protection level, the final UW, or the final effective protection level, UPF, sorry, the final effective protection level you are going to achieve between point A and B is important for you. And this effective protection level is a sum of the voltage drop at the line L1 here between the point A and the SPD, plus voltage protection level of the SPD, plus the voltage protection or the drop of the voltage drop at the line 2. So basically, the actual voltage goes into your equipment, or the voltage which is threatening to your equipment is a combination of the entire voltage drop or the voltage potential difference between the point A and B. The condition which we are supposed to meet is UW and the UPF. We need to have a relation. This is very important. UW has to be always greater than the effective protection level. If the effective protection level is larger than the UW, of course your equipment will fail. The definition of effective protection level is voltage at the connection point of the SPD assembly resulting from the voltage protection level of the SPD with possible disconnector and the wiring voltage drop in the lead, the connections. So that means the actual voltage which is going to stress on your equipment between the point A and B. This is actually a very important point when you select and install an SPD. Say, for example, in the picture you are seeing an SPD. You can find this kind of installation in several hundreds of locations or probably thousands of locations in India. A 4-pole SPD is connected and the line length is almost about 3 to 4 meters. If the line length is 3 to 4 meters, you can forget about the SPD. This will be only Nam Kevas. It won't work. Another case, large line and the SPDs are connected. So when you connect an SPD, you have to be equally, when you select the SPD, when you select a good quality SPD, you have to be serious about the connecting wire length, and you should always use the appropriate recommended length. If you are using a longer wire, effectively the effective protection level is high. As a result, your equipment may not get protection. We will come to this point later, but before that, there are two types of connection recommended in this standard. This one is called as connection type 1 or CT1. In the standards, you will be able to see as CT1 means all the live conductors. See, line conductor and live conductor, these two are different. Line conductor means RYB is line conductor. Live conductor means RYB and neutral. All the four are live conductors. In this particular case, between the live conductors and the earth, 4 SPDs are connected, and this is called as 4+0 network. Means between the live conductors to earth, the SPDs are connected. The next connection is called as 3+1. In this case, 3 SPDs are connected between line to neutral. In the first case, as I said, 4 SPDs are connected between live conductors to earth. In the second case, between the line conductor and the neutral, there are 3 SPDs, and between the neutral and the earth, there is one more SPD, and this is often called as 3+1 connection. Both these connections can be used depending upon your network, like whether you are using a TNS network, TNCS network, TT network, or IT network, and depending upon the voltage stress, the temporary over voltages expected in the network, you are supposed to select one of the connection. The conditions which you always try to meet is between live conductors and PE, that means the connection type 1, this is called as common mode protection. Between live conductors means, you see, the first one, between live conductors and PE is the earth. This is called as common mode protection because lightning is trying to increase the voltage or trying to differ the voltage of earth with respect to the live conductors. It's a common mode phenomena. If you connect SPDs between live conductors, like between R2I, B2I, R to neutral, neutral to B and all, this is called as differential mode protection. The condition number 1 is protection between live conductors and PE is compulsory, especially at the origin of the installation. Protection between line conductors and neutral is recommended to ensure equipment protection. You see, at the origin of installation, the purpose of installing SPD is to divert the lightning thread or the lightning current. Most often for larger building, your equipment are further inside the building. So if your equipment are inside the building, the second line, protection between line conductors and neutral is recommended to ensure equipment protection. That means the CT connection type 2 probably is required near to your equipment. Now, protection between line conductors is optional. Some equipment may require both common mode protection and differential mode protection. Common mode means all the 4 current carrying conductors with respect to the earth. Differential mode protection means between the lines. Some equipment require both common mode protection and differential mode protection in order to have impulse withstand and the impulse immunity. To ensure overall protection against transient voltage protection due to switching or from the atmospheric origin, where this is applicable, both common mode and differential mode protection is required for example, class 1 or class 2 equipment with FE connection. I'm sure most of you are following our programs quite regularly. So you know what is a class 1 equipment, you know what is class 2 equipment, you know what is FE, functional earthing. So for sensitive electronics, either class 1 or class 2, sometimes you require both common mode protection and differential mode protection. Here, the connection type 1, the protection level between all the live conductors and the earth, I have put as UP. Now, in the second case, you have between the earth, as I said, in the first condition is there shall be an SPD between all the live conductors to the earth. Now, in the second connection, between the phase and the earth, you have actually 2 series connected SPDs. The protection level of first set of SPD plus the protection level of the second set of SPD is actually the effective protection level, including, plus the voltage drops on the wire. So effectively, if you go for a connection type 2, you are supposed to add the protection level between two different types. So the recommendation given in the standard is where protection between line conductors and PE is provided by a series connection of SPD, protection mode, for example, single mode SPD is line to neutral plus neutral to PE according to connection type 2. This series connection shall fulfill the above voltage protection level requirement. Where such combined voltage protection level between line conductors and PE is not provided in the data sheet of the manufacturer, it shall be calculated by addition of the voltage protection level given in the individual SPDs. It's very easy to understand. If the manufacturer gives a test certificate saying that the connection CT2 between phase and the earth, the device is able to provide a voltage protection level of less than, say, for example, 1.5 kV, you can accept it. If the manufacturer is not providing that particular parameter, you should add the protection level of the first set of SPDs plus the second SPD. So say, for example, 1.5 kV in the first case where I am moving the cursor plus 1.5 kV in the second case. So the effective protection level of both the SPDs itself will be about 3 kV plus the voltage drop of the connecting wire. So basically there is a risky situation if you don't select the correct SPD. The next condition, it is recommended that the voltage protection level provided by SPD does not exceed 80% of the required rated impulse voltage. What does? Very simple, I explain. You have a class, a device with impulse voltage withstanding of, let us say, 4 kV. You have an MCB DB and the voltage impulse withstanding is 4 kV. The standard recommends that you select and install SPDs in such a way that finally the SPDs are not allowing the voltage more than 80% of the withstand voltage of the MCB. Let's say 4 kV is the 100% withstanding, 80% is something about 3.2 kV. So the protection level, effective protection level provided by your SPD must be lesser than 3.2 kV. So these conditions always we should read carefully and we should select. It also means before buying an SPD, please go through the specification of the SPD. We have to be very careful. SPD is a new product in the market. Nowadays, all of you know that the most important style of business is you buy something from China, you put the Chinese certificate, you put the label on the product, you put a brand name, and then balance, nice catalog and sells. Actually, with respect to SPD, it's really risky because SPD is a product which is going to create a short circuit, which we will discuss in the next slide. So basically, current rating of the SPD is selected based on, say, various parameters. Voltage rating of the SPD is also selected based on various parameters. So in a larger industrial installation, selecting and erecting SPD is an engineer's job. The person who is, or the company who is doing it, they have to be really technically qualified to do it. Now, the next problem is a temporary overvoltage. Temporary overvoltage can be experienced in a low voltage electrical line due to various reasons, such as a fault on the high voltage system, an earth fault on the low voltage system, a short circuit on the low voltage system, and the loss of neutral. Loss of neutral means a neutral disconnection in a three-phase line or in a three-phase service connection. So all these 4 reasons could create temporary overvoltage, means a voltage higher than the normal operating voltage. Let's say your normal voltage is 230 volt. Instead of 230, maybe 300, 400 volt will exist in the line, between the lines, or probably between the line and the earth for certain time, not continuous, but for certain time. These are temporary overvoltages. And the temporary overvoltage withstanding capacities are very much specified. The requirement of SPDs are very much specified in the standard. I'm not going to explain it. My I will explain how this is applicable. One of the TOV, because all the TOVs together is again a big subject. The temporary overvoltage with respect to neutral disconnection. I am showing you a three-phase network, line 1, 2, 3, and a neutral. You have a single phase equipment connected to this particular line. Between the L1, L2, L3, you have 400 volt, perfect. Between the lines and the neutral, you have the 230 volt. I am sure there is no confusion on this particular case. 400 volt between the lines, 230 volt between the line and neutral, but 230 probably it is not 230, it may be 240, 400 maybe 415 or 440. That is not the issue. But in a normal condition, your voltages are stable, and now you see three SPDs are connected between line and neutral. The applied voltage into these SPDs are 230 volt. As a result, in normal condition, your SPDs are in good condition. It is ready to work. But whenever there is a neutral disconnection in your circuit, you know very well that the connected line, between the connected line and neutral, suddenly the potential is 0. As a result, the disconnected part of the neutral with respect to the other phases, suddenly the potential is 440 volt. As a result, the 440 volt stress is on the SPD, and this 400 volt stress probably may kill the SPD within a short time. Most of the cases, SPDs are failing in India because of temporary overvoltage, not really because of the surge current. It is most of the time because of temporary overvoltage. As I said, there are 4 chances of temporary overvoltage, and I have put only 2. Mr. Dominic, you have raised your hand. Any point to my? I hope my.
No. You go ahead, Gopakumar. Nothing.
Yeah, thank you.
I don't know how I raised that. I just lower that. Okay.
Yeah. So these two SPDs between L1 to neutral and L2 to neutral are suddenly stressed with 400 volt. As a result, these SPDs will fail. I am just going to show you how this failure occurs in a network. Now, as I said, most of the time failure of SPDs are due to such unnecessary situation. It is not a transient situation. SPDs are not supposed to protect, or it is not designed to protect your electrical installation from a TOV. Because of these SPD failures, the IEC, the testing standard, had introduced a test. 120 minutes TOV test is recommended in the IEC standard. The background of this particular test is lot of cases SPD failures are creating fire or explosion. SPD is for safety, and these devices shall not create a hazard. As a result, the additional tests are included in 2013 or 2014. What the test recommend is the combination of the SPD along with the fuse. It shall not flash, or it shall not create a fire, or it shall not explode is the requirement. Now, the video, how this is happening, you can see a video. This is a typical case of SPD failure due to temporary overvoltage. This is a petrol filling station. The previous day, something happened in the power supply. Something happened in the power supply. The neutral was disconnected. Without understanding the problem, they are trying to switch on the power supply. Please have a look. Yes, this is how it explodes. These two technicians, very courage. They are afraid of the blast, and they are trying to run away. So, such failures or such disasters also can happen because of an SPD. And what IEC had recommended is an additional test, means a TOV test. Say, for example, line to neutral connected SPD, you make 230 plus 10% into 1.73, approximately 440 volt between line and neutral. In a worst condition, up to 440 volt can be expected for a longer time. So the standard says your SPD, you connect between 440 volt supply for 2 hours and ensure that the SPD is not blasting. SPD can fail, of course. SPD can fail under a safe condition. Safe fail is accepted. The second condition, SPD may withstand this 120 minutes, 440 volt. These two conditions are accepted. The SPD which is blasting or which is catching fire are not suitable to sell in the market. These tests are has been included and recommended in the standard, but as we always know, in India, such new techniques are introduced quite late in the market, probably after 10-15 years. So in our case, when you select the SPD, please ensure that your SPD is able to handle one of these. Fail safe means under a TOV condition, your SPD will fail, but it cannot catch fire. Let it fail, but it shall not create a hazard. Number two, the SPD can withstand. That means nothing happened to the SPD. SPD is still strong. So these two SPDs, of course, commercially, the second one will be a little bit expensive. The National Building Code 2016 also says that the SPDs shall withstand a TOV for 120 minutes. All SPDs line to neutral and neutral to earth shall have visual indication, shall have remote signaling facility, and so on. So basically, these safety features are already included in the standard. Now, the next interesting subject, priority to continuity of supply or priority to continuity of protection. Actually, this is a very tricky subject. It is easy to understand, but little bit tricky to understand. One of the very important subject with respect to the safety of SPD, because every SPD at the end of life, it may create a short circuit. And on that particular time, a backup fuse, a fuse is required, as I shown here, a fuse is required to isolate the SPD from the circuit. Now imagine you have a line, you have the earth, I put an SPD, and if this SPD is creating a short circuit, actually you are going to be in trouble. So in order to avoid the short circuit, I have put a backup fuse. In the second case, I put the backup fuse on the line. In the first case, I put the backup fuse on the SPD circuit, whereas in the second case, I put the fuse on the line itself. The first one is called as a priority to continuity of supply. It means at the end of life of the SPD, probably after 5 years, after 7 years, or even after 20 years, at the end of the life, this SPD is going to create a situation of a short circuit. And if you have an SPD, a fuse, in this case, the fuse had isolated the SPD from the circuit. As a result, your circuit is safe. The problem is there is no SPD. Once when the fuse is burned, there is no protection for your equipment, but the continuity, the supply is continuing. Supply is still going into your equipment without protection. And this is called as priority to continuity of supply, because in the first case, your priority is not protecting the equipment. Your priority is to have continuity of the supply. In the second case, at the end of life of the SPD, the fuse will blow. And once when the fuse blows, there is no power supply to the equipment. Imagine between the line and the earth, you have an SPD which is always in the short circuited situation. Most often it is in the short circuited situation. Under this, we cannot find out whether it is really short or whether it is open or whatever. But a fuse is required. Under the hazardous situation, end of life, the fuse is gone. In the second case, there is no supply, but there is, your equipment is still protected, and this is called as a priority to continuity of protection. While selecting and installing an SPD, you must select the option whether you wanted to go for priority to supply or priority to protection. Very important question to be asked to the user. If you wanted to have both priority to continuity of supply and protection, then you have to go for an SPD under this condition. That means there are 2 fuses and 2 SPDs connected in parallel. One of the technique which can be used is we have got an SPD with two numbers of discharge devices inbuilt. Let's say, for example, initially the SPD is green. Once when one of the MOV fails, the color changes to yellow. And only once when the second SPD fails, the color changes to red. So once when the SPD changes from green to yellow, you get time, you can replace the SPD, and basically you don't go into a situation that your equipment is unprotected. So this case, the third case, is applicable where continuity of supply and the continuity of protection is necessary. But as I said, here there are SPDs we have which can have multiple channels, and the channels actually it ensures continuity of supply and protection. So basically, these three questions are very important. Now, the first two questions, priority to continuity of supply and priority to continuity of protection, how these are applied and the backup fuse is selected. SPD and backup fuse is always a complicated subject because the manufacturer says more than 125 amps a backup fuse is required. But always we try to, in the next slide, I explain what you should understand is, in the line, you have an OCPD, overcurrent protective device, and you can have an additional protective device for your SPD. But once when you put additional devices, please understand that the line length is more and more the effective voltage which goes into your equipment. We are actually stressing more voltage to the equipment. The effective protection level is also low. Most of the time, the dendril mounted SPDs are tested with the GLGG fuse. If you look at the manufacturer's catalog, you can find it. GLG is nothing but HRC fuse. So additional fuses are required under certain conditions. Let us look at what are the conditions with which additional fuses are required. Now I am showing a picture. Here on the line, there is an 125 amps fuse. Let us imagine the manufacturer told that the SPD, it's a type 2 SPD, maximum backup fuse is 125 amps. And so normally we say that SPD doesn't require a backup fuse if the line current is up to 125. Unfortunately, as I said, this is a little bit technical subject and it is very tricky to understand. So probably you may not be able to visualize what exactly I am talking. I'm so sorry for that because the subject is in that way. So you have an SPD. SPD manufacturer says that I need a 125 amps backup fuse. Less than 125 amps, I don't need a backup fuse. Higher than 125 amps, I need a backup fuse. Now imagine on the line there is a backup fuse and the line fuse is 125 amps and the SPD manufacturer says no additional backup fuse is necessary. In the second case, even though the line fuse is 125 amps, I am putting an additional backup fuse. Let us look at how these two cases are working during the end of life. In the first case, once when the SPD is at the last day of working, the end of life, this fuse will isolate the supply. So continuity of supply is gone. You don't have continuity of supply. Of course, SPD probably is able to disconnect without the help of the fuse, but the wording which is written in the standard and in the manufacturer's catalog is maximum backup fuse is 125 amps. That means if the backup fuse is higher than 125 amps, SPD is going to blast. The 125 amps fuse have got a certain amount of energy with which it is going to disconnect, and the SPD is able to handle only that much energy without a blast, and you cannot increase the capacity of the backup fuse. You have a 125 amps fuse at the end of life of the SPD. This 125 amps fuse is out. As a result, the continuity of supply is gone, but continuity of protection is still there. Now in case 1, no continuity of supply. If you wanted to have continuity of supply, F2, you have to use the second connection diagram. The ratio between F1 is to F2 is 1.6 is to 1. So If you wanted to have a continuity of supply, you must have an SPD, and the ratio of F1 is to F2 is 1.6 is to 1. That means you have a 125 amps fuse at the line. Your continuity of supply is important. You must put an F2 mandatory, and the rating of the F2 is about 60% lesser than 125 amps. Probably a 63 amps fuse will do the job. So if continuity of supply is important, irrespective of what is written in the manufacturer's catalog, you must require a backup fuse, which is with this ratio you should select. I have some more examples. So the first one, continuity to priority of protection. The second one, continuity of priority to continuity of supply. As I said, these two subjects, it's a little bit complicated to understand. One moment, please. Yeah, in the first case, where the continuity of protection is important, means once when the SPD fails, the fuse is out. As a result, there is no power supply, but the equipment still is protected. The second case, there is a backup fuse for the SPD. Once when the SPD is out, or once when the SPD ends its life, the F2 disconnect the SPD from the line so that the equipment is unprotected, but the supply is still continuing. Under this condition, imagine the SPD manufacturer says my backup fuse is 125 amps. Why I am saying 125 amps is actually most of the SPDs available in the market nowadays claim 125 amps fuse, which is actually not applicable for the SPD which we are selling. We are selling SPD recap from Germany, and those SPDs have, you can go for up to 315 amps backup fuse. Now imagine with the 125 amps backup fuse, F1 is to F2. If F1 is less than or equal to 125 amps, you don't need any F2. If F1 is higher than 125 amps, then you require an F2 of 63 or 80 amps. F1 is the line fuse, F2 is the additional backup fuse. And if the line fuse is anything greater than 250 amps, you require an F2, and the maximum capacity of F2 is 125 amps. That is the meaning, maximum backup fuse 125 amps. It doesn't mean that always up to 125 amps you don't need any backup fuse. You can take it in that way. Up to 125 amps you don't need any additional backup fuse, but then you are going to achieve the priority to continuity of supply. You are compromising. What you are going to achieve is priority to continuity of protection. Your protection is achieved, but the supply is a small issue. Now, the second case, here in the second case, priority to continuity of supply means under any condition, the supply shall not be interrupted. In this condition, if the F1 is 63 amps, F2 is 32, always you require an F2. If the F1 is 100, F2 is 63, F1 125, F2 63 or 80 amps, F1 more than or equal to 250, F2 is 125 amps. So while selecting and installing an SPD, please be very careful, find out what priority you have, and based on the priority, you select the appropriate fuse. The rating of the fuse in case of the SPD which we sell in the market, the rating of the fuse is a little bit different. It's not 125 amps, it is actually 315 amps. But again, the method of selection remains same. Now, in a circuit, if you have an SPD with the long connecting wires and with a fuse, actually we are stressing, we are putting more pressure into our equipment. In the previous slide, I have shown you the effective voltage protection level. Effective voltage protection level means the actual voltage which is going into your equipment. Let me show that picture again. Here, the effective protection means the actual voltage between the point number A and point B. It consists of the protection level of the SPD, voltage drop on the connecting wires, voltage drop on the D is nothing but the extra fuse which you are going to install in your line. So all these things are actually affecting your the ultimate voltage which is going to stress your equipment. This particular test report is the first one. The blue color line shows an SPD with a connecting wire length with a backup fuse, and these two are the actual voltage, the actual effective voltage which went into an equipment with a bus bar mounted SPD. Say for example, at 20 kiloampere surge current, these two SPDs, which are actually bus bar mounted SPD, no backup fuse and no connecting wire directly on the bus bar, the actual effective voltage protection level is something about 1 point or lesser than 2 kV, let's say 1.5 kV. Actually, these SPDs are protecting your equipment. Whereas in comparison, if you have a DIN rail mounted SPD with the long connecting wires, let's say 250 mm or so, the actual voltage goes into your equipment, the effective protection level which goes into your equipment with a surge current of, during a surge current of 20 kiloampere is about 8 kV. So as a result, technically speaking, achieving safety is very difficult. So most of the time, even if you go for a good quality SPD, the connecting wire and the backup fuse decide the actual safety. And most of the time, we are compromising the effective protection level because of the line length and the backup fuse. This is a very important subject which I wanted to explain you. The solution is to go for an SPD which is bus bar mounted. For example, you connect it directly on the bus bar. There is no line length. Since there is no line length, the voltage drop on the line is absolutely zero. As a result, very good protection level is achieved. Or you go for an SPD with the integrated backup fuse. Integrated backup fuse means this is an SPD, a type 1 and a type 2 SPD, which is having a backup fuse inside. An integrated overcurrent protection means you doesn't require an additional backup fuse, provided your fault current is, or your expected short circuit current is lesser than 100 kiloampere for 1 second. Under that condition, you don't need any backup fuse. These devices have fuses inbuilt. All the complication of backup fuse selection and all the complication with respect to the length of the wire can be easily or simply solved with this kind of SPDs, modern SPDs. But you must understand that a type 1 SPD with integrated fuse probably is 50% expensive than the type 1 SPD without this feature. But instead, rather than looking at the cost of the SPD, performance wise, this will be absolutely of a high quality. You can save space of your panel board. You can save the space of your backup protection, the wire length. As a result, effectively, this is going to be much more better in comparison to a conventional SPD. So with this, I would like to stop the presentation. So during the first part of our presentation, we discussed something about what kind of SPDs are there, type of SPDs, spar gaps, GD tubes, and so on. In the second part, we try to explain 2-3 other subjects, such as how the current carrying capacities are selected, voltage protection level, and so on. With this, I would like to end the presentation. Thank you very much. We can go for the question and answer session.